Thank you, everyone. Hopefully you had a great break. So I am Chong Ma. I'm the research associate leading the Sturgeon Lake transect based at Laurentian University. So I have a lot of contributors, as you can see here, and many organizations have helped our project in Sturgeon Lake. So in this talk, I'm going to talk about the geologic background at the very beginning, then the reflection seismic survey along our transect, followed by MT data and a interpretation of the crustal structure along our transect. Then a 3D view of the regional structure based on our result and also those from the nearby lithoprobe data. And then I'm going to talk about the basement rocks and partial melting events based on geochemistry. And lastly, tectonic evolution of the region. So first, on this regional geologic map, I just want to highlight that the Western Superior in this region was assembled roughly in general from North Caribou southward. So we have North Caribou separated by English River sedimentary terrain, then this Winnipeg River continental terrain, and this little Marmin terrain, continental terrain, which including this Western Wabigoon oceanic terrain. And further to the south, we have Quatico sedimentary basin and Wawa oceanic terrain. So this study focuses on the easternmost part of the Western Wabigoon terrain, and we will be looking at 3 transects, one from our Med-Earth project here, Sturgeon transect, and 2 from previously completed project of the lithoprobe transect. Here you see WS1A is only showing a part of it because I don't need to interpret the rest of it for my study area. Another one is east-west oriented WS1F transect from the lithoprobe. So here we are looking at a detailed geologic map of the Sturgeon transect area. This transect is represented by this blue line. So 2/3 of the transect is within the Western Wabigoon terrain, and 1/3 is within the Winnipeg River terrain to the south. So in the Western Wabigoon terrain, we have 4 major green schist facies metavolcanic assemblages of 2775, 2745, 2735, and 2720 million years old assemblages, and which are accompanied by some volcanic intrusions. That's largely represented by 2 phases in this map area, which are 2735, excuse me, and 2720 million years intrusion. Also, there are a lot of post-tectonic intrusions. And economically important is the South Sturgeon assemblage in this part that hosts several past producing VMS deposits that is represented by the Matabi mine, that's a major one, producing zinc, copper, lead, silver, and gold. Structurally, in the map scale, it is folded, but the microscopic folding is not very common at smaller scales. Then there are 2 major deformation zones, this Sturgeon Lake shear zone and this newly discovered southern Sturgeon shear zone here. So the Sturgeon Lake fault zone is characterized by shortening along the center segment and oblique shearing to the southern and northern segments, whereas the South Sturgeon shear zone is characterized by oblique strike slip shearing with different like various components of shortening at different segments of the shear zone. Then to the south, the Winnipeg River terrain has biotite quartz feldspathic gneiss and foliated tonalite, then thin tectonic tonalite and granodiorite with post-tectonic hypotassium granitic and alkali intrusions. And interestingly, all of those three lithologies have amphibolite blocks within it. Then the major deformation zone between the Western Wabigoon oceanic terrain and the Winnipeg River terrain is constrained to be between 2700 and to 2695 based on previous study. So on the cross section along the Sturgeon transect, it is clear to see the belt quartz felsic gneiss as rafts in thin tectonic granitoid. They are about 1 to 5 kilometers long and have different strikes and dips. So the attitude of the fabrics right now doesn't represent their initial attitude of the fabrics. In the Western Wabigoon terrain to the north, the yawning directions of the paleo-basalt and graded volcanic beddings support the map scale syncline that has a east-west orientation for the exoplane, which is centered roughly here on top of this brown unit. That's the youngest sedimentary basin, Amen Bay assemblage, which is the focus of our master project here in this region. Then there are stitching plutons intruded the two ductile shear zones. For example, the Bell Lake and the nearby granitic plutons intruded this South Sturgeon shear zone. So those magmatic bodies can constrain the timing of deformation. So next, I'm gonna show you the reflection seismic survey along the transect. Here is the pre-stack migrated section of the seismic data. This seismic profile is about 70 kilometers long and 48 kilometers deep. So 7 zones of distinctive reflectivity are identified on this section. In the lowermost part, zone A is featured by weak horizontal reflectors. And from 10 to 40 kilometers, there are 3 zones of about 30 to 35 kilometers thick. Zones B, C, and D. They jointly show prominent and gently dipping reflections. Then the south dipping reflectors in purple here in zone C distinguish it from the 2 surrounding zones. Then zone E is poorly reflective with a few random reflectors. Zone F here is mostly poorly reflective, and there are minor strong reflectors, plus a few south dipping reflectors in purple, similar to those below it. And zone G is characterized by subhorizontal anastomosis reflections. And importantly, in the middle part of the transect, the reflection moho is less prominent and deeper beneath zone C than the surrounding areas. And the 2 faults here, F2 and F3, are identified on the basis of outcrop data and truncation of reflections. So next, I'm going to show you our interpretation of the seismic profile. So because the reflections in zones B, C, D, and EF are generally similar, they are considered to be a common basement rock, which are largely similar to the rocks identified on the outcrop above zone E, which are Winnipeg River terrain. So we think the prominent reflections indicate gneissic fabrics and mafic layers, whereas those poorly reflected zones represent granitoid layers and bodies. Collectively, they are probably Winnipeg River terrain of gneisses and granitoids intruded by younger granitoids. That's post-tectonic. Then the south dipping reflectors in purple exclusively above this crustal root right here in the middle part. are interpreted as mafic, ultramafic decks imaged by outer-plane seismic ray. So this apparent crustal root is evidenced by the upper Moho, and we think it is likely caused by partial melting of mantle rocks that would result in interlayered felsic and mafic rocks, similar in reflectivity to that of lower crustal rocks. Therefore, now they are continuous. And zone G represents the minimum thickness of Sturgeon Lake greenstone belt. And this reflective pattern does not represent the actual fabrics of the greenstone belt. The basal boundary of the greenstone is considered to be between the bottom of zone G and above those prominent reflectors in zone F, because two lines of evidence. The first one is shortening and sinister strike slip components on outcrops of F2 and F3, and the lithology structural fabrics of the greenstone belt are steeply dipping, that is discordant with those of the basement that is shallowly dipping. So the basal boundary of the greenstone belt in Sturgeon Lake region is considered to be a thrust fault zone. So next, I'm going to show you the MT data along our region. A broadband MT survey was conducted along the seismic line. So the cross-section of a three-dimensional inversion model along the transect is shown here in the upper panel. The warm colors represent conductive zones, and the cold colors represent resistive zones. So in the lower panel, that's our interpretation, we can see a continuous low resistivity zone of less than 300 ohms from Moho beneath the middle segment of the transect to middle crust along the entire transect. Then the bottom of C1 conductor, that's the main conductor, extends to depths of 45 kilometers at least. That bottom is overlapping with this seismic crustal root. Then there are a few seismic, conductive fingers in the upper crust, represented by this C1C conductor here. Then the high resistivity of 10 to 100,000 ohms in the upper crust in blue, that's at first glance, it's similar, but if you look at the scale underneath the greenstone belt here, it's larger than 30,000 ohms, whereas the rocks below the greenstone, below the Winnipeg River terrain, it has less than 30,000 ohms. So here are the representative horizontal slices of the 3D model from 3 kilometers get deeper and deeper down to 58 kilometers. So you can see this continuous conductive zone can be picked up from 5 kilometers, and it's well shown starting from 8 kilometers here, continuously down to the uppermost mantle. So because the transcrustal conductor spans from Moho through the entire crust, it is likely caused by a combination of multiple factors that influence electrical conductivity at different crustal levels. An important feature is that the bottom of C1 conductor overlaps the apparent crustal root, which suggests that the formation of the conductor is related to the formation of the crustal root, which is melting of mantle rocks, as previously mentioned. We interpret that the upper crustal conductive fingers to reflect high air content in mafic silicates and interconnected sulfides, which is highly possible because the underlying crust underwent extensive partial melting, as shown later in this presentation. So if we look at this air magnetic map directly above the conductive finger C1C here. There are VMS deposits represented by the triangles and very strong high magnetic bodies, likely caused by the high iron content in alkali plutons. So the mid to lower crustal conductor is interpreted to reflect by two factors. The first one is interconnected green boundary graphite films in reduced environments. The second one is diffusion of hydrogen that is an incompatible element in nominally anhydrous silicates, which are crystallized from magmas formed by partial melting of crustal or mantle rocks. So combining all the data sets so far, we can have a overall understanding of the crustal architecture underneath the Sturgeon transect. First, the Sturgeon transect, the Sturgeon Lake greenstone belt is about 5 to 10 kilometers thick, separated by a thrust fault zone with the underlying ground basement. The basement is characterized by gneissic fabrics from mid to lower crust of probably paleo to Mesoaquine gneisses and granitodes, as we observed on the surface of this part of the basement rock, which is demonstrated by the zircon data later in this presentation. Then the crust was extensively overprinted by new Archean syn to post-tectonic magmatism in the orange color here. That was characterized by hydrogen and carbon-rich silicates and formed by partial melting of mantle crust rocks. Then the partial melting was likely triggered by subduction-related fluids and melts. Why? Well, so first, partial melting of mantle that is now the crustal root here could produce first interlayered felsic and mafic or ultramafic rocks in the crustal root to form the reflectivity similar to the lower crust. Second, the mafic melts to form dikes above the crustal root, just above the crustal root, not in the area surrounding the crustal root. And felsic melts in the crust above the crustal root to form the C1 conductor. So the second evidence is that there is a probable relic subduction zone. So under the crust about 20 kilometers to the south here, based on the lithoprobe data. So combining the two reasons, we think it's related to the subduction. So next, I'm gonna try to construct a 3D model for the regional structure. We are very lucky that there are two nearby transects from the lithoprobe data in our area. Here is WS11A, a part of it, north-south orientation. It's about 70 kilometers in Sturgeon Lake and Savant Lake area. Another one east-west orientation, that is WS1F line, extending about 90 kilometers just north of the Sturgeon transect. So here is a composite crustal section of Sturgeon transect and the partial WS1A transect. It beautifully shows some of the key interpretations. First, continuous distribution of the greenstone belt in the upper 5 to 10 kilometers of the crust. And second, a collision zone in the mid to lower crust, represented by the poorly reflective zone and discordant reflectors. A transcrustal fault zone F1 here from in the mantle all the way beneath the greenstone belt and eventually on the surface that accommodated the deformation between the terranes. Then here subcreated crust in the mantle and an apparent crustal root beneath the crust, overlain by the greenstone belt, probably produced by the thickening crust at that moment and partial melting of mantle rocks. So combining the three seismic transects in this region, we are able to construct a 3D model of the structure there, containing 140 kilometers from along north-south direction and 90 kilometers along east-west direction. So this model reveals a new arcane convergent belt between the main Winnipeg River to the north and the proper continental margin to the south, represented by north-south convergence and a lactonous greenstone belt in the upper crust, collision of gneissic basement in the mid to lower crust, and northward subcretion of crust, and a transcrustal fault zone of F1 here. So next is some initial result from basement rocks. We collected 12 samples from the Winnipeg River terrain here, and some representative photos showing coeval formation of biotite tonalite and gabbro, and blocks of foliated tonalite enclosed in gabbro, and blocks of gneiss in post-tectonic tonalite, and partially melted gneiss here, and gneissic fabric, including K-spar-rich layers in pink here, and ductile ridge in groove lineation on gneissic foliation. For each sample, we did a careful examination. We filtered all the suffered with lead loss and high discordance. This particular sample is very interesting because the morphology and the trace element data shows those zircons in the core, excluding the rims. The cores are metamorphic zircons. That dates the metamorphic event at 2900 million years. And the rims represent later partial melting events, younger than that age. So combining all the 12 samples, we have 5 major peaks of ages. The first 2 peaks at those ages represent the protolith, supported by trace element and the Hafnian data. Then metamorphism at 2.9 billion years, and the major partial melting events in the younger events. Then if you look at the protolith, it has evolved Hafnian isotopes. At 2.9, there is a big jump of Hafnian isotopes. After that, it's juvenile events. So significant input of juvenile magmas since 2.9. That's a critical moment. If you look at I'm gonna skip this one. Basically, we wanted to understand the evolution of the magma from 3 billion years to 2.7, because you can see the trace element data are very different. So we use this ratio to represent evolution of heavy rare earth element. This ratio to represent evolution of light rare earth element. So overall, magmas with more fractionated rare earth element progressively increased over time. Then the temperature, water content, and oxidation depth all show some interesting trends, which are outlined here. And the water content and temperature, increase of water content and the decrease of temperature over time seems to match pretty well. So overall, the tectonic evolution in this region, here is a regional map, a cross section along this line, Sturgeon Lake and the surrounding greenstone belt are here in the upper crust. So if you look at the entire crust column, we have multiple very old crust, partially melted at multiple times, then later again partially melted to form 2.7 billion years old melts. It's a continuous process. 2 pieces of protolith at 3 billion years and 2.9 billion years, then metamorphic event at 2.9, followed by episodic partial melting events. And the major dominant partial melting event was at 2.7 billion years. So here is just the composite cross-section highlighting the important result of the combined data set. overall, this work favors a model of subduction of the original Winnipeg River terrain.
Hey, Chong, you got to wrap it up.
Collation of the, original subduction of the Western Wabigoon terrain, followed by collation of the Winnipeg River terrain. So subduction was ongoing at this time, 2.7, among those two subduction zones. Here, the Wawa subduction. So the coeval development of the two subduction zones might indicate the cratonization in this part of the superior was partially contributed by accretional orogenesis. So I'm gonna leave this here because I think I'm run out of time. Some work my master student did this past summer, then the future work focusing on the greenstone belt.
Yeah, you're gonna have to leave it there, Chong. Thanks, we need it. There's lots of progress in the chat room here, but is there any live questions to ask Chong? Okay, Chong, this is from Zuzi. Is there any possible model to explain the foliation pattern distribution of the gneissic rafts? Possibly earlier deformation that predates the greenstone belt?
The gneissic, there's the fabric patterns of the gneissic rafts. They are random, like from this raft to the other one. But within the individual raft, they are similar, very consistent fabrics. So I think those fabrics were formed during the formation of the gneiss, but later intruded by younger post-tectonic magmas, which interrupted the original fabrics. So I cannot draw any conclusion from the fabrics of the gneissic rocks for the history of the original basement rock, unfortunately.
Okay. Chong, can you comment on the moho being lower in the central portion of your section?
Yeah, it's very obvious along the Sturgeon transect, and it seems continuous to the north under the lithoprobe transect. Because it's this crustal route it's perfectly match the south dipping reflections that we interpret as mafic dikes. So we think the formation of this crustal route is related to those dikes, and that can be constrained or can be interpreted by partial melting of the uppermost mantle rocks in this part. Then I'll look at the literature. There is a possible relic subduction zone about 20 kilometers to the south. So that seems to provide the flows and the partial melt from the subduction zone to trigger the partial melting of the uppermost mantle. So this is a very important source for materials and metals and fluids from the mantle to like pour into the crust above it to trigger the continuous and episodic partial melting events, including both mafic and felsic in rocks, including the alkali intrusions of the Sturgeon Narrow and the Bell bodies.
Okay, thanks, Chong. There's we'll have to move on now, but there's an awful lot of traffic in the chat room. Maybe you can go in and.
Sure. I'm gonna work on it right now.